Hi guys, welcome to Learning Electronics Repair. So, quite a catchy thumbnail there, yeah? They're all wrong. You can't test MOSFETs with these things that you might want to use. I'm sure plenty of you have these sort of things. Good old multimeter. And you will probably say, well, I use these to test MOSFETs. Yeah. And you know what? So did I. And I probably still will to some extent, but the problem with these is that although they will tell you if a MOSFET is good, they will not tell you if a MOSFET is bad. And not only that, but they may well tell you that a good one is bad as well. Okay, so I'm going to demonstrate this in this video. Watch it through to the end. I'll try and keep it relatively short for you guys. And then let me know your thoughts down there. Were they all wrong when they told you this is how you test a MOSFET? Okay, let's begin. And here is where our journey starts. So this is a Class D amplifier out of a subwoofer. In fact, it's two amplifiers. This is a bridged amplifier. So we have, you can see, Class D amplifier chips basically driving pairs of MOSFETs, and the speaker is connected between the two amplifiers. It's bridge, so there's one large 18-inch speaker inside the subwoofer. This is the actual subwoofer amplifier, so DAS Avant 18A Class D power amplifier, 750 watts. Okay. And on here we have an input board, the amplifier, which I've taken from there, and a power supply. So the power supply gives about plus and minus 90 volts, something like that, and that actually powers the amplifier. And there's a bit of a history with this one. So this was originally faulty. I had a few of these to repair. I repaired the other ones. This had blown transistors in the power supply, MOSFETs, and also blown short circuit MOSFETs on the amplifier as well. Okay, so I replaced the MOSFETs on the power supply, powered it up on the bench, and after a few seconds it blew up again, even with the current limiter on it. And having then checked everything on this power supply and not finding any reason, I came to the conclusion the only other thing left is that the MOSFETs, which I had fitted to repair it originally, were fake. I ordered some more MOSFETs from somewhere else, put those in, and it then worked fine. Yeah. So originally faulty, blown MOSFETs. I put new ones in, thinking they were fine. They were fake. And the fake was just a guess because I couldn't find anything else wrong with it. Replaced them again, it's fine. I then had a problem with the amplifier module. This also had short circuit MOSFETs. So again, I ordered some, put them in. It worked, so I powered this up on the bench at fairly low power. I don't have large speakers here, but I could see it was working. Both amplifiers were working, driving in bridge mode, and it went out to the customer. And shortly after it came back, and he said this thing was working and it got so hot, smoke came out of it. Smoke, the magic smoke. So of course I looked at this again for him. It was working on the bench. Once again I put it on low power, it was working, but the heatsink was getting very hot. Even at low power this was getting really hot. And I wasn't sure, I had the thermal camera, if it was one of the MOSFETs getting hot or all of the MOSFETs getting hot. So I took the PCB off this metal bracket cum heatsink that's bolted to the metal plate on the back of the subwoofer. The whole thing forms the heatsink. I took the board off and I powered it up on the bench, again just at low power. And I could see that with the thermal camera, all of the MOSFETs were getting hot. And while I was doing that, one of the channels stopped working. So although it was bridged, I was actually just using each channel individually on a speaker each, and one of the speakers cut out, it went off, and then I discovered that one of the MOSFETs had gone short. Now it wasn't mounted to the heatsink, but I wasn't driving this at any amount of power either. So I came to the decision that probably I had fake MOSFETs on here as well. The ones I'd ordered for this were also fake. And that brings us to today. And I will say straight away, this video is not necessarily about fake MOSFETs. It's about what I found when I got some MOSFETs from somewhere else, another supplier. They came from the electronic shop up in the capital, Las Palmas, okay? But he only had 2 new ones and 2 pulls. Yeah, pulls have been taken from something, salvage ones, okay? The other 4 here are 3 of them which were in the amplifier when it went pop. 1 that wasn't in the amplifier but from the same batch, so I actually bought a batch of 5, okay? And the 5th one is short. I'm going to show you now. Testing the short one is really easy. Okay, so we can see that is obviously short. The multimeter will tell us, the component analyzer will tell us it's short. The problem is with these, so let's have a look at them. So, if you want to test these MOSFETs, and you've learned how to do this, maybe you've seen YouTubers telling you how to test a MOSFET, maybe you've seen me telling you how to test a MOSFET, and I will admit now, I was wrong as much as all the other ones of them are wrong, okay? You would probably use a component analyzer or a multimeter. So we have 8 MOSFETs here which are not short. 3 came out of the amplifier, 1 was from the same batch that was never fitted, 2 are new ones from the store, and 2 are pulls from the store, okay? Now, we can have a quick look at them, because we should check, are the markings all the same? Are they all the same type of MOSFET? Well, let's check that. Well, these are the 4 that came out of the amplifier, or rather 3 that came out with the white dots on, and 1 from the same batch that I bought, which was never used, okay? And you can see FB23N20D, International Rectifier logo, and they've all got the same date or batch code, 218P77WS. So these are all from one batch, and these are from AliExpress. And these 4 are from the electronic shop in the capital. You can see IR logo again on these 2, 23N20D, Y1W9. The cross is not to say that they're faulty, it's just so I know which ones were the new ones from the store, okay? And then these 2 are also from the store, but these were pulls. So we have one marked B23N20D with a different logo. Okay, it looks different to the other ones. Okay, and then we have this one also, FB23N20D. Logo looks somewhat different again, and these are not the same batch, these are different to each other, okay? So that's what we have. Now, let's test the ones that I put in the amplifier. In fact, let's test all 4 of these. To save mixing these up, 1, 2, 3, 4, okay? Help you guys keep track of where we are. So we'll use the peak analyzer first. Number 1. Good. Yeah, good. Gate threshold 2.09. It just gives me the test current, 2.5 milliamps. That's basically what it tells me. So it says it's good, and that's the gate threshold. That's the voltage at which the MOSFET switches on, okay? Number 2. Okay. Again, is good. Gate threshold 2.09. Same test current, so that's good. Number 3. 2.13, slightly different gate threshold, but only 0.04 of a volt difference. I mean, that's as near as damn it the same, yeah. Number 4. Good. 2.13. So they're all good, according to the analyzer. We can also test these on the other component analyzers to save time. You've seen they all work, so I'm just going to put one of them in. One where the legs are easy to insert, in fact. So this is the El Cheapo component analyzer. Okay, so N-channel MOSFET. gate voltage threshold of VT, it says here 2 volts. It's telling me the same thing. That's fine. Here's the Fernesi analyzer, LCRP1. We'll use the same MOSFET. Let's see. Yeah. This is telling us RDS on 0.2. Okay. And it's telling us the threshold voltage 0.98. Right. So this is giving us a little bit more information. And of course the multimeter technique. Diode mode. So red to the drain, black to the source, nothing. All the way around we will see the parasitic diode. Okay, diode junction. And from the gate to the source we don't see anything in either polarity. And the same to the drain, we don't see anything in either polarity, okay? But what we can do is turn the MOSFET on. So red to the drain, black to the source, nothing. Touch the gate with the red, back to here, and it's switched on. Reads short. And it reads short now in both directions because it's on. Okay. So that is a good MOSFET according to the multimeter. Again, we can put the black lead on the gate to switch it back off again. And it's off. So according to all the test equipment we have, they're fine. But something is wrong with these because they get extremely hot in the amplifier once it's running, and in fact one actually blew up. Now let's look at the MOSFETs I got from the electronics store. So these are the 2 new ones. We'll do the same tests. I'll put some numbers on them, 5, 6, 7, 8, okay, and the ones with the X on are the new ones. Peak analyzer, test. Diode or diode junctions. Diode or diode junctions. Just check I have all the leads on in the same order as before. Yeah, all connected properly. Try again. Diode or diode junctions. And that's saying anode to the blue and cathode to the red. So anode to the drain, cathode to the source. What that is seeing is the parasitic diode inside there, okay? Try the next one. Analyzing. Diode or diode junctions. Same. So the peak analyzer says they are faulty. Let's look at the poles. So these are from the same place, but they're not from the same batch. These are second-hand ones. You would think these are more likely to be genuine ones. Okay, let's see. So same. You think that's strange? So I have 2 new ones, and I've tried one. Let's try the other used ones. And they're all faulty. Well, this thing's normally pretty damn reliable, but maybe it's just been silly. Yeah. Let's try one of the other analyzers. Here's the Fernesi. This gave us more information previously, so let's see what this says about. Okay, number 5. Unknown component. Maybe I have a bad contact. Let's just go again. Diode. Yeah, that's saying the same as the peak was saying. Diode. Number 6. Again, maybe just got a bad connection there. Try again. Diode. Okay. So this is telling me the same thing that the peak said. No difference. We may as well do the rest of them. Number 7. Diode. How about number 8? Diode. Do you suppose the El Cheapo will do any better? Think this will do any better? Well, I'm not going to hold my breath, I'll tell you. Don't hold my breath. Diode. 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 So, all the component analyzers say these are faulty. Maybe we'll have better luck with the multimeter. So, same method as previously. Diode mode. Nothing. Parasitic diode. I'm sure because that's what the analyzer sees. Parasitic diode. Okay. From the gate to the source. Nothing. Gate to drain. Nothing. Gate to source. Should switch it on. Let's see. No, it doesn't switch on. So, the problem with these MOSFETs is that the gate doesn't work. Yeah, it doesn't switch on. I'll just try another one. I'm sure I could go through all of them, but we'll do the same with this one. Number 8. Nothing. Parasitic diode. Try to switch it on. Nothing. Nothing. Oh, this one does something in the reverse direction. So that's different to the previous one. This is one of the poles. This is one of the new ones. How about this one? This is the new one. So again, nothing. Parasitic diode. Try to turn it on. Doesn't turn on. Okay. And the other pole. So this one again, nothing. Parasitic diode, try to turn it on. Yeah, that also does something, but gives a completely different reading to that one. So those do something a bit different. Okay. Maybe there's something strange about these MOSFETs. Something in the design of them. Maybe they have some internal components or something in there which stops them being measured by the multimeter. But having said that, they're all the same sort and they read just fine. Let's look at the data sheet. And here it is. So IRFB23N20D, HEXFET power MOSFET, 200 volt MOSFET, 24 amp, 0.1 ohms or 100 milliohms, RDS on. Interestingly, the Finerity told it was 0.2, which is well out of spec. It's double. And that was on the ones which I suspect are fake. It won't even read the other ones, it just thinks they're diodes, okay. So that's just a plain and simple MOSFET. Yeah. Nothing weird in there, no internal resistors or something strange, yeah. There again, so they seem to be okay. So why are our MOSFETs from the shop all faulty? Yeah? Why are they faulty? Well, let's investigate. And this is my fake MOSFET tester, which is a project I've been developing, sponsored by PCBWay.com, although this video isn't, by the way. So, fake MOSFET detector, deluxe version. I made a more basic version. I haven't uploaded this yet as a shared project on PCBWay.com because I'm still developing this. I've been working on it. But these PCBs do work, by the way. So, in the video where I showed you guys this, I actually gave you a link to my Google Drive. On there you have the Gerber files, the list of components or BOM, bill of materials. You have everything you need to work on this, and I uploaded those in a format that you can import into a CAD program, whether you use KiCad or EasyEDA or whatever you use. You can import this project, you can change and modify it to your own needs. You can then create your own Gerbers, or you can just use the Gerber file I've given you. Go to PCBWay.com, instant quote, put the Gerber file in, and you can order these PCBs. So this is the deluxe version. I'm just going to show you on paper how this basically works, because it's a very simple device in actual fact. You can build this or something similar without using a PCB or the switch. Yeah, a very simple version. Let me just show you that. In its most basic form, what we have is power supply. I use my bench power supply, 0 to 30 volts, variable current, variable voltage. Okay, we have resistor, and this goes to the MOSFET you want to test. So this is the drain, source, this goes to ground. Okay, so this is plus, this is 0 volts, and then we have the gate, and the gate goes to 2 resistors like so, and the resistors are the same value as each other. I'll give you the values in a moment. There's also from here a Zener diode. My deluxe version has multiple Zener diodes and a switch, but the basic version we use a 10 volt Zener. Okay, the reason will become apparent if you watch the rest of the video. These 2 resistors, the value doesn't particularly matter greatly, but they need to be the same as each other, and they need to supply enough current for the Zener to work and not to be such a low value that the Zener would burn up. And on mine, these are 1.2k. The brown doesn't come up very well on this camera, but 1, 2, 0, and one more 0. Okay, 1k2, 1k2, and that is the tester. This resistor needs to be something more than 20 ohms and less than 30 ohms. It needs to be in that range to use the tester as a 1 amp tester. And this is the original one I built. I used 4.7 ohms, 5 of them in series, you can see there. Okay, power resistors 10 watt each, so it gives a total of 50 watt dissipation, and 5 times 4.7 gives me 23.5 ohms, which is right in the range I want it to be. Okay, and on my deluxe version I have 3 more resistors, so 100 watt, 7.5 ohms, 3 of them all in parallel with each other, and when you press the switch, it switches these to be in parallel with that lot. Okay, so you got 23.5 ohms in parallel with that and that and that. And we can be lazy and use an online calculator, or we could just measure this one I built. But using the online calculator, we have 7.5, 7.5, 7.5 and 23.5 all in parallel, gives 2.26 ohms. And you will see that 2.26 ohms is basically 10 times less than that, as near as damn is okay, and that gives us the 10 amp range. So depending which resistor I switch here, which load, I can either test this at 1 amp or 10 amp. Okay, so you could build this very simply just like this: Zener diode, 2 1/4 watt, half watt resistors, and some power resistors and a switch, and you've got one built. Okay, all you do with the switch, switch on off, that goes to that set of resistors and back to the power. Okay, so it just switches those however you do it in parallel with that. As long as you end up with somewhere between 2 and 3 ohms, it will work fine. Try get it close to that. Yeah. My tester, by the way, also has LED here, Okay. But again, this is optional. If you want to fit it, I'll show you in a minute what it does. The resistor, of course, is to stop too much current going through the LED. I used a 2K2. And the LED should be red if you do fit one, because it has a lower turn on voltage than, for example, a blue or a white. Yeah, so red. There is one other difference with this version. This will switch between testing N channel and P channel. This will just test N channel, but they're the most common. If you do want to look at the schematics for that version, the link is in the video description down there. How does the tester work? Well, basically, you set the current limit on your power supply to 1 amp. You start with a voltage of 0 and you gradually increase the voltage until the MOSFET switches on. You'll see that because the LED lights up. But I found a better way of doing that. I'll show you. Because we have two resistors of the same value, the voltage on the gate will be half of the voltage you set your power supply to until this reaches 20 volts. Okay, once it reaches 20 volts, the voltage here will get to 10, half of that. The Zener diode will conduct and it'll keep the voltage at 10. So you can turn this up as much as you like. Now to maximum, this will not go more than 10. So the gate voltage will be 10. Once you get above about 23.5 volts, the current limit will kick in because you now have 1 amp flowing through here. And this will allow you, first of all, to measure the gate threshold voltage, the turn on voltage when the LED comes on, and it will allow you to measure the RDS on when the gate voltage is 10. And that's important as well. The way you measure RDS on, by the way, with this, I need to draw something else. You have a connection from here. This is your multimeter to ground, red, black. Okay. And when the MOSFET is fully on, 10 volts on the gate, whatever you read on here in millivolts will equal whatever the RDS on is of the MOSFET in milliohms. Okay, that's on the 1 amp range. In the 10 amp range, whatever you see in millivolts, you have to divide it by 10, and that is milliohms. So that's how you use it. I have the gate voltage set to 10 volts. Why 10 volts? Well, let's have a look at a datasheet for a MOSFET. And here we can see that the RDS on max for our MOSFET is 0.1 of an ohm. And we also see that the gate threshold voltage is between 3 and 5.5 volts. Also, the maximum RDS on of 0.1 of an ohm is measured with these parameters. So we have the voltage on the gate of 10 volts and the current through the drain of 14 amps. Now, our tester will allow us to test these MOSFETs, in my case, at a current of 1 amp or 10 amps. The reason being, my power supply, well, it only goes up to 10 amps. But if I had a more powerful bench power supply, say a 20 amp one, then I could reduce the value of the load resistor by half and test at 20 amps. All the data sheets I've seen so far test the RDS on with 10 volts on the gate, which is why that was the voltage I have my tester set to, and also why, if you're making a fixed voltage one, to use a 10 volt Zener. Now we have to take care of temperature. So when we test these MOSFETs, especially at 10 amps, they're going to get hot. I mean, just think about it. So even with an RDS on of 0.1 ohm, okay, at 10 amps, the voltage across the MOSFET is 10 divided by 0.1, which is 1 volt, and multiply that by 10 amps, and that's 10 watts, and that's for a very low RDS one. Yeah, if this was like 0.3, it's 30 watts. Okay, so you could do this many ways, but the way I'm going to try it is obviously fit the MOSFET onto this small heatsink you can see, and I have a plastic tub, and I'm going to fill that with water, not to the top, but enough so I can just drop this in. The water will come across there somewhere. So even if the MOSFET tried to fall in, which it can't do, it can't end up in the water, okay? And we'll test it that way, and let's see how well this works. Now you might think, well, I'm only going to test this for like a second to get a reading, which is a fair comment. But there's another issue here. So the RDS on of a MOSFET increases with temperature, and this thing will get very hot fast. So you probably can't get a realistic reading unless you try to keep it at an even temperature. So let's try this technique, but I'm sure this will work absolutely fine. It's probably the cheapest and the easiest way I could think of doing it. We can connect this to our tester. Now you'll notice the meter connections are here. This is where you would measure the voltage across the drain source. But remember, I'm using some extension wires here, so they will have some resistance as well. And at high current, you want to measure the voltage here directly across the MOSFET to get a realistic reading. So I'm going to attach my meter directly across the MOSFET, like so. No problem if I short this out, by the way. The current limiter on the power supply won't pass more than 10 amps, okay? We've added some water, okay? No high voltage here, so if I knock it over, can't really damage anything, he says, okay? We have the multimeter on volts range. I'll switch the power supply on, which is here, set to 0 volts at the moment, okay? I'm going to set the current limit to 1 amp, so I'm going to connect the two leads together. Turn the voltage up a little bit. We have 1 amp. And now we can test our MOSFET. I've connected the power. Now we're going to turn this up until the LED lights. There. You see? And we find just the point where the LED lights. Now. And that is telling us 4.3. Okay. You see the LED is actually just off. I can actually do this by watching the current on my power supply and turn this up until it just starts to pass current. It's just switched on now. A little bit more. So we can see at 4 volts it's just starting to conduct. The LED won't come on until we go a little bit more. There. Which is 4.4 divided by 2 is 2.2. So it looks like we can say that the threshold voltage of this is half of that, which is 2. And that is well out of spec for our MOSFET. Our MOSFET should be minimum 3, maximum 5.5. So that isn't a good sign. Now let's turn this up until we get 1 amp. So we just turn the voltage up. The current limiters come in. And we can see 0.125. Okay. That is the RDS on 0.125 ohms. Again, that is a bit higher than the spec would say. Okay. You can also see this is dissipating 23 watts of power. That's why we need the high power resistors, which are fairly warm. But our MOSFET is nice and cold with the water there. Let's do a 10 amp test. So to do a 10 amp test, we set the switch. Yes, it's back to front on mine. That is 10 amps. We turn the current up to maximum and we just turn the voltage up. So this won't affect the threshold voltage, the turn on voltage. It will affect the RDS on. Let's see what we get, okay? 1.7, 1.8, and it's climbing. So even in the water, that was starting to warm up. At 10 amps. So it's giving us 1.7, 1.8 at 10 amps. Now remember, at 10 amps you need to divide that by 10. So it's about 0.18. So that MOSFET is out of spec. The RDS on is too high. Should be 0.1, it's 0.18, you can see. And the gate threshold voltage should be at least 3, it's 2. Let's try one of the other ones. This is one of the new ones. I put an X on them. According to our component analyzer, these are faulty. According to our multimeter, these are faulty. Let's set this back to 1 amp. So we'll turn the current down, we'll switch it on, and we'll increase the current to 1 amp. Okay, 1 amp we have. We'll connect our tester, and we'll turn the voltage up until the LED lights, which is there. Or again, we can just watch the current on here if we don't use the LED. So 11.2 is the threshold voltage for this, much higher. Divided by 2, so 5.1, and the data sheet says 3 to 5.5. So that is well within specification. It's towards the high end, but it's in specification. And this should tell you why the component analyzers, nor my multimeter, can test these MOSFETs, because they can't generate enough voltage on the gate to turn it on. Therefore, it's a diode junction. Yeah, that's why it doesn't work. This is what people have not told you, okay? I've told you now. And I've learnt myself now, okay? So I won't feel smug about it. Yeah, I've learnt also. So we can see this is within the spec for the part. Go back to here. So again, we're going to turn this up now until we get 1 amp, and we're going to measure the voltage across the MOSFET, okay? 0.08. That's less than 0.1, so that's good, yeah? Let's try it at 10 amps. So we set this to the 10 amp position. We turn the current up to maximum. And we go again, and let's see what we read. This will increase because this will get hotter, but let's see, yeah? 1 divided by 10 for the 10 amps is 0.1. So that is bang on specification, okay? Let's try one of the pulls. Okay, so this one is number 7. It's one of the 2 pulls that we have. Let's have a look. LED is lighting at this point. We can see the current is here. Just starting to turn on. 10.6, so that's 5.3. That's within spec. 5.5 is maximum. Okay, now we test RDS on. 0.08, again, well within spec. And we try that at 10 amps. So we go to 10 amps, we turn the current all the way up on the power supply, and we watch it, okay? And remember, again, we need to divide this by 10. Okay, so what do we get? 0.98991. Again, obviously, as it starts to warm up, it will increase a bit. So that, again, is within spec. So, guys, as I said at the start of this video, you can't test MOSFETs with a component analyzer or a multimeter. Well, you can, but you can't always. So we had a situation here where we had 4 new ones, or at least 2 new ones and 2 supposedly known good used ones, and they were all testing as bad. Yeah, I put them on my tester. Not only do they all test okay, so we know they are in fact okay, we can also see that the gate threshold voltage and the RDS on are within spec, so they are good original MOSFETs. The other ones, well, the component analyzer said they were fine, yeah, but the gate threshold voltage was 2.2, which is well out of spec, minimum of 3, and the RDS on at 10 amps was about 0.18. It was almost double what it should be, and that's why they got hot and burnt out in the amplifier. Because, as I explained before, with 10 amps, RDS on of 0.1, you get 1 volt across the MOSFET, so 10 watts. At 0.18 RDS on, you get 1.8 volts across the MOSFET, and that's 18 watts. So they're dissipating pretty much twice what they should do. They're getting twice as hot as they should do because of the high resistance, and that's why the thing failed. Yeah, smoke coming out. Okay, guys, so lots to talk about there, and we're going to chat down in the comments below. What do you think? But I'm going to stand by my point. If you want to test MOSFETs, especially power MOSFETs, you've got to do it this way to get anything like a sensible result. Okay, hope you enjoyed that, and I look forward to seeing you all soon again on Learning Electronics Repair. Ciao for now, guys.